Welcome back, everybody. We have a question for Fall 19 Test 1 Part 4 mechanism. The student wanted us to do this last part. The question is, what's going on? Is the O disappearing? No, the O attached to the carbon with two methyls is still an O attached to the carbon with two methyls in both products. So please don't protonate the O. The reason we protonate oxygen is to make it go away, make it a leaving group. Don't do it. What else can you protonate? Strong acids need to protonate something, don't they? We're going to protonate the alkyne and make a cation here if we put the H on the end, or a cation on the end if we put the H in the middle. And that seems to account for both products. So that's what we're doing in step 1, protonate an alkyne, just like an acid-catalyzed hydration. Ooh, that's lazy. We don't like lazy arrows. Hits the H, sigma becomes lone pair. And we are generating phenyl attached to C double methyl OH attached to C double C. Copy paste with a plus sign. One of them has the cation here. Lazy again. And one of them has the cation here. Why did this one become the cation? Because there's two H's here now. There used to be only one. A new H went on the end. Why does this one have the cation here? Well, it's still got one H, but there's an H here that wasn't there before. That's where the H went. And both of them have lone pairs on O, which can attack the carbocation carbon. It's going to generate an oxonium that looks a lot like the conjugate acids of our two products. What am I having to do this? Sure. This one will go to phenyl CHC. We can put the double bond going that way. One, two. Something's not right there, is it? Is that right? No, that's not right. This one goes up here. Whoa. And we have a bond H. We attack the end carbon. When we attack the middle carbon, we get phenyl. There's the O. Dimethyl oxonium. And how do we make this into that product, which I would probably have to circle? Explain my choice. It's not about carbocation stability, is it? You'd have to compare this and say, this one's more stable than this because it's more hyperconjugated, because it's more substituted. But then you realize, wait a minute, I just circled a product that has ring size 4 if you circle this one by mistake. That's highly strained. I don't think carbocation stability is going to overcome the fact that you made a ring with a lot of strain. So my explanation, I know I'm not finished the mechanism, is that there's less angle and torsional strain. Those things we mentioned way back in Organic 1, they never go away. Small rings, size 4 and 3, suffer from angle and torsional strain. And the way to get to those two products is simple acid-base chemistry using the conjugate base of hydrogen or sulfuric acid, also known as hydrogen sulfate. And same here. Lone pair grabs H, Sigma becomes lone pair. Lone pair grabs H. Sigma becomes lone pair. And you got your products. And that's page 8 of 10. We're getting there. And we did that one, page 9 of 10. Ah, yes, some NMR stuff here and NMR stuff here. How do we get product 4 from the 4 reactions? Oh, we got a lot to do. Let's go. What do we have? Yeah, if we don't know how to draw this one, we can't really do this question. So where do we start? It's kind of like nomenclature mixed in with NMR. Nomenclature mixes in with everything, right? That's our language. So you draw benzene first with iodines on carbons 4 and 5. Iodine, iodine. And on carbons 1 and 2, so 4, 3, 2, and 1. 1, 2, 3, 4, 5. Same group. So if we can do it once, you've got to draw on carbon 1 an ethoxy group. Remember, always start with the end. There's an ethoxy group on carbon 1 and on carbon 2. O, there's an ethoxy group. O, that's an ethoxy group. Ethyl oxygen, ethyl oxygen. Carbon 1 of the group is here. On carbon 2 of the group, there's a 2-tert butoxy. On carbon 2, there's a tert butoxy. That's another oxy. Tert butyl group with an oxygen, and then it's attached. So now we can finally do the question. I definitely will see one very large singlet representing all 6 of these carbons. They have no neighbors. Okay. I'll see a triplet here. How come? 2 neighbors. They're here. This one, 2 neighbors. Where are they? They're here. Same story for the same group. And these are singlets. There's no neighbors. There's no H here. There's no H here. And there's no H here. And there's no H here. So just singlets and triplets. And how many? Signals. Remember, there's symmetry in this molecule. So let's just do half the molecule. And then we've got the number of signals. And I'll put a highlighter on the unique carbons. There's one unique carbon. There's another unique carbon. There's another unique carbon. Whoops, I missed. Another unique carbon. Another unique carbon. And these are all the same. And how many highlighters do you have? This is the same as this, so I don't need to do it. Sorry, this is the same as this. My little divider didn't really divide in half, did it? There, a little better. This is the same as this. This is the same as this. This is the same as this. So on and so forth. I missed one. Oh my goodness, I would have had the wrong answer. All that hard work. That's the frustration with multiple choice. I missed this one entirely, didn't I? So the highlighters are for the unique types of carbon. Each one of them is duplicated on the other side. 1 signal, 2 signals, 3, 4, 5, 6, 7. So 7 signals and singlets and triplets. Singlets and triplets, 7 signals. Oh my God, how do you even find the right answer there? It's AC. And we're doing okay. It's 6 minutes. 6 minutes. We're supposed to be done at 5. I think we can do it. Maybe. We'll see. I wrote product 3 here. And how do we get product 4 from 4? Which ones do you, and now we know we use all the reactions, right? Always use all the reactions. Don't pick and choose which ones you think are important. They're all important. DHP, dihydroparan and sulfuric acid, is going to protect this. We have to do that so that we can deprotonate an alkyne, pKa 25, and not an alcohol, which would normally deprotonate first, 17. So we're protecting it so it doesn't have a proton. All right, so steps 1 and 2, protect the alcohol with a DHP. Look back at the start of today's notes if you want to see what a protected alcohol looks like. And then we're taking the H off here to make an anion, which attacks formaldehyde. So we're going to get a new carbon. And then aqueous sulfuric acid does many things. It protonates the O- that this becomes, and it deprotects the dihydropyran group from here. So you get this OH back. So product 3 is going to look like everything we see in blue stays. The OH, we protected it and then deprotected it. So it's back. And down here, up here, over here, phenyl. But the exciting part was when we made a bond to a formaldehyde, which became an O- after you attacked it. There's the C. This C here is this C here, became an O-, but during the sulfuric acid deprotection, we also protonated. So both these H's came from the sulfuric acid. And that's your product. And what is closest to the KEQ for the acid-base reaction in step 2? Potassium hydride. So we got H- plus a terminal alkyne. You're talking about a 25 going to a 35. KEQ is -10 or +10. Sorry, 10 to the 10. What am I talking about? 10 to the -10. This answer, 10 to the negative that. And this last one, I know we're running up against time. It's okay. Well, when you're going to, hey, we learned that diazomethane with alkene makes epoxides. And the groups, if they're on the same side of the alkene, they end up on the same side of the epoxide. So we can call those both wedges. Got an isobutyl here and an isopropyl here. And we got our epoxide here. Not epoxide, sorry, cyclopropane. And we got H's that were also on the same side. And you make a 50-50 mix of this and the one where these are both dashes and these are both wedges. And now the thing is, this is a question of stereochemistry. And without doing, taking all the time to do the stereochemistry, I'm just doing it ahead of time. You got 1, 2, 3. It's S over here. And you got your 1, 2, 3. It's R over here. Let me verify the S. 1, 2, 3, S and R. So it'd be the structures that had SR and then RS. So we don't like RR and we don't like SS. 50-50, 2 and 3. And that is the answer. It's all about stereochemistry. Okay. And that is today's Q&A. Now, I think we lost everybody. So I was going to ask for you to email me questions if you have them, but everybody's busy. You don't have